Cement is one of the most vital yet invisible materials in modern civilization. Though hidden from plain sight within concrete, steel-reinforced cement enables the construction of bridges, skyscrapers, dams, and countless other structures that make up the foundation of the modern world. But how is this seemingly mundane gray powder produced? In this exploration, we will follow the cement-making process step by step, unearthing the answers to this common question. Limestone and clay are the two primary raw materials used to produce cement. Limestone is an abundant sedimentary rock composed mainly of calcium carbonate. Clay, which consists of hydrated aluminum silicates, provides the silica and alumina needed to generate the desired clinker minerals during cement production. To obtain these materials, controlled explosions are used to blast bedrock from quarries. The limestone and clay are then loaded into trucks by heavy excavation machinery and transported to the crushing facility. At the crushing plant, the rocky chunks of quarried limestone and clay are fed through a series of crushers to break them down into smaller fragments. The crushing process typically involves a primary crusher, secondary crusher, and even tertiary crusher to achieve the desired size reduction. The crushed materials exit the final crusher onto conveyor belts that carry them to the raw mill storage domes. To produce cement, the crushed limestone and clay must be combined and pulverized into a fine powder called raw meal. Conveyors transport the crushed limestone and clay into measured hoppers where the materials are mixed to the proper proportions. This raw meal mixture is then fed into the raw mill, which contains a large rotating steel drum. Powerful steel balls within the mill pulverize the raw meal into a fine powder as the drum rotates. The fine raw meal powder exits the raw mill and enters the preheater tower. As it passes through this tall vertical tower, hot exhaust gases from the kiln below heat the powder to around 1,000 degrees Fahrenheit. This preheating process initiates the beginning stages of calcination. Calcination refers to the dissociation of carbon dioxide from the calcium carbonate in the raw meal, yielding calcium oxide, also known as lime. The partially calcined meal then enters the kiln from the top of the preheater tower. Fuel is burned at the lower end of the kiln to generate immense heat reaching over 2,600 degrees Fahrenheit. This extreme temperature kicks the chemical reactions and clinker formation into high gear. As the raw meal slides down the kiln, it forms condensed minerals called clinker. Clinker consists primarily of hydraulic calcium silicates, aluminates, and aluminoferrates. These hard granules form the active ingredient that confers cement its binding properties. The hot clinker spills from the lower end of the kiln into a clinker cooler. Cooling the clinker prevents undesirable crystal formations while preserving clinker quality. The cooled clinker moves to the cement mill, where gypsum and supplementary materials like slag, fly ash, or limestone are added. This mixture passes through a final grinding stage to achieve the fine, powdery finished cement. The gypsum controls the setting time of the cement. At this point, the cement is rigorously analyzed in the on-site quality control laboratory. Technicians run chemical composition analyses and physical tests on the cement to ensure it meets all the necessary quality standards before being approved for shipping. Though cement itself is a key building material, it mainly serves as the binder for concrete. At concrete production facilities, the precisely measured ingredients of cement, water, and fine and coarse aggregates like sand and gravel are combined in mixing trucks. Admixtures are added to adjust setting time, workability, and properties like strength. The freshly mixed concrete is transported to construction sites carefully placed and compacted into forms or molds. Proper curing by maintaining the right moisture and temperature is essential to allow full hydration of the cement and gradual strength gain in the concrete. The versatility of concrete, enabled by the controlled production of its constituent cement, makes it the most widely used building material in the world today. While most of us rarely ponder the hidden material that binds our concrete infrastructure, cement is a modern engineering marvel that enables the urban landscapes and towering structures of our modern world. The next time you walk into a building or over a bridge, think about the tiny cement particles within those slabs of concrete that made it all possible.